Hello everyone. Today we're going to be talking about tokenization. And if I was to do this in person, I would hand out this short 2-page paper to you, but it's available to you in Learn. So by the end of the lecture, you'll probably want to go and pull that up and be able to refer to it as appropriate. In reading, catch you up. Again, largely you can figure out what it is to read in the course based upon what I'm talking about in the course textbook. Again, I'm going to primarily often refer to the search engines, Information Retrieval and Practice by Croft, Metzler, and Stroman. And I might refer to the other textbook at times, but at the moment, most of the references will be out of here. But I really want to encourage you to be able to dig into both of these, all right? Be looking for the material. This is sort of the bare minimum to read. So this is, you have to read this stuff, to really be following along and to fill in any gaps that might be in the lecture. But the real idea of a course like this is to try to absorb as much as you can. Hopefully you find it interesting and you want to learn more. And there is just so much more to learn. And so yeah, it's basically, this is not all of chapter 4. You could read on, all right? Same thing with chapter 5. And then, yeah, same thing with chapter 5, I guess. And so basically, in chapter 5, you're reading the first part of the chapter, and then here, just these subparts of subsections of section 5.3, and then section 5.5, and again, just these two subsections of 5.6. And this is largely going to cover the material that I'm going to talk about with regard to tokenization, and then this is going to move you into the next topics, which are dealing with term statistics and then indexing. All right. So yeah, our next topics will be things like term statistics and indexing. All right. So let's dive into tokenization today. And yeah, so I will tell you what to read in lecture. So that's where the announcements of what reading material is. Okay, the tokenizer. So it's the software that we're going to use, the algorithm that we're going to use, whose goal is to break a document into tokens, which just is basically saying a bunch of strings, because a document, as we know, it's one long string, a whole bunch of characters, letters, numbers, punctuation, spaces, all sorts of stuff. It's just one long string. To us, we see it because we've learned how to read. We break it up into words that all has meaning to us and so forth. To a computer, it's just a string of characters. So it needs we need to give it an algorithm to basically break it up into tokens, which are also called variously as we go through the course. You'll see at times referring to them as terms or words. Tokens are perhaps the most appropriate thing to call them, because we could have something where like, that's not a word, but it is something that we've broken the text up into and stored, and we're using to associate that string with a document. It's one of the many strings. Okay. All right. So token is perhaps best so that you don't fall into the illusion that we always have perfect terms or words associated with these documents. We won't. we're going to have these strings that we've computed and associated with these documents. All right. Now, most of the time they will look like words, so that's good, but they aren't always perfect words. So we certainly shouldn't think of them that way. One thing I want to note right now up in front so that no one thinks otherwise is our tokenizer is going to be, so we'll apply it to a document to break it up into words. We are also going to apply it to whatever our user's query is. And so we're going to be having users put in natural language text. We're not going to be supporting any fancy query languages or anything. We're just going to say put in some text. And so we're going to kind of end up in, for our search engines, we're going to be treating the query that someone puts in as like a really short little document. And we're going to apply our tokenizer to that and produce a bunch of tokens. We will then take those tokens and the tokens in a document and applying an algorithm that we could call a similarity algorithm. It measures effectively a score, which is like the similarity between the little document that the person supplied as their query and the document that we have stored in our index. Then we're basically able to compute that for all the documents in an efficient manner, and the documents that are most similar to the query are the ones that we're going to show the user first in the ranking. Now, it's not just always a notion of a similarity. The ranking measures go beyond just notions of, oh, this is similar. So it's not simple matching. But for us to do things, we will be matching the tokens from the query with the tokens that we have in the documents and counting various statistics and things like that. And so it is very important that we apply the same scheme to the user's query. And the idea here is so that the tokens match those in the document. All right. One of the things that we're going to have, we're going to see when our basic tokenization scheme is that we're going to downcase or lowercase, use lowercase, for example, lowercase the terms, the tokens. So if we downcase all the tokens in a document, but don't downcase a query, there's no way. So let's say someone, as part of their query, they put in all capitals USA. So there's no way USA could match anything and could match any document. Now this might seem a little premature to be talking about what to do with the user's query, but I want to get this idea in your heads now that whatever scheme we apply to documents, we apply that same scheme to the queries. This is one of the biggest mistakes students make in building search engines is they think, oh, I'll do something different for the query. And then they don't understand why the quality of their search engine is horrendous. Well, it's because they have, like, we talked about vocabulary mismatch in a previous lecture. So again, vocabulary mismatch is where I come up with index words to describe something, you come up with index words to describe something. We're unlikely to be using the same words. So we'll have a mismatch in our vocabulary. This is the way humans are. If you do something like this is like an algorithmic mismatch, vocabulary mismatch. It's like, I programmed the computer so that they wouldn't match. I mean, you wouldn't do that on purpose. It's entirely a mistake. But for some reason, it's not obvious to a lot of people that this would be the wrong, that they have to do this. They'll do something different and they think it might improve things. It will not. You want to do the same thing. All right. Or if you're not going to do the same thing, it's something deeply intelligent with regard to your knowledge about how the tokens are created in the documents. But in general, the thing to do is apply the exact same tokenization scheme to the queries as to the documents. All right. So in this course, we are going to use a very simple tokenization scheme. And this is the basic outline of the scheme. As I mentioned, the first thing that we're going to do is downcase the text. Okay, and so what this means is to convert all letters to lowercase. Now I will mention, so if we had Mark, it becomes all lowercase. All right. So I'll mention though, if it's not clear, everything here is being taught with regards to English retrieval. I actually don't know for the languages that don't use similar characters. Do they have capitals, uppercase and lowercase? I don't know. I don't do foreign languages for retrieval. Certainly, researchers around the world do work on other languages other than English. I think one of the things that's going to be important to note before I go through this small example is the concepts that we talk about are absolutely end up to be the same. So whatever the language is, for the retrieval methods that are in use, you still have to find a way to break it up into some tokens, into some units of meaning, things that mean something. Okay, so you got to chop up that long string of the document or whatever it is into pieces, usually. Okay, that's usually the case, that we've got some linear thing and we need to chop it up into pieces. And then we're going to do various other things to those pieces, some other transformations and stuff, and then we're going to end up with a final result. That final result is then what we're going to index and use in our ranking algorithms. And people do this in all sorts of languages, and the same concepts are at play, but the details are, of course, different because the languages are different. Anyway, so we could have a name, such as mine. We capitalize names, proper nouns. And to downcase it, we convert all of it to lowercase. These are already lowercase, so it's just the first letter that changes. What sort of advantages why would we be doing this? So advantages to downcasing, a great thing is the user does not need to be careful. With case in their query. And you can certainly think about, a lot of times you're like, do I really need to be bothered with hitting the shift key? I just want to tap in a word and hit search. Like, does it really matter? Imagine if you always had to think carefully about it and to think, ooh, let me get the capitalization right for exactly what it is that I'm looking for. So that's a nice, it's a small thing, but it's handy. But perhaps one of the other nice things is in English, all of our sentences start with a capital letter. So this allows us to match words at the start of a sentence. So we might put in a word with lowercase as a user, because why would we a lot of the words we're going to use are not proper nouns. Why would we capitalize them? But a lot of those words could very well be the subject of a sentence. As a subject of a sentence, it might very well be the first word. And as the first word of a sentence, we're going to capitalize it in our documents, unless we're E. Cummings and doing poetry or something. So we don't want to, if we don't do that, all of those capitals in words capitalized at the beginning of sentences form a different set of words from all their lowercase usages throughout the document. So when we decide we're going to end up counting how many times we see a word in a document, we'll have a count for the word with its capitalization and a count for the word with it lowercase. The user puts in a query, they might do lowercase, and we're only going to be counting the number of times the lowercase word is. Those are the matches we're going to find. We're not going to find any of the capitalized matches. That seems really weird. That doesn't seem like a good idea. So that's probably one of the biggest things, all right, is in English we start sentences with capital letters, and this is a way to fix and deal with that issue. You could envision other solutions to the problem, but this is a really easy solution. What sort of a disadvantage might this have? Well, this is going to lose the ability to discriminate or distinguish certain acronyms and proper nouns. So you might very well, though, we talk about the easier for the user and stuff. But what if you were looking for a town where I spent a lot of time as a child, Pleasant Valley. So I didn't live in Pleasant Valley, but I had a high school in it. So Pleasant Valley, this is in Iowa. There's probably lots of Pleasant Valleys. But boy, Pleasant Valley as a proper noun is quite different than you might find in text. People talking about things being pleasant, and they might talk about valleys. Oh, wait a minute. If I query with capital letters, because as a user, I know I want the town, I'm looking for things about Pleasant Valley, this could really be a helpful hint to the search engine, because it will only get positive matches with index terms on documents if we had kept the capitalization. Okay, so it's like, if we had kept the capitalization, we would be able to notice and recognize that this document is referring to Pleasant Valley as a proper noun. So we could hone in on and help you find what you're looking for. When we gain the advantages of downcasing, for a query like this, we hurt the user, because now we're going to match the words pleasant and valley all throughout the collection, and not just only when they're capitalized, which is a hint that they're being used as proper nouns, rather than just at the start of sentences. So this is, again, this whole trade-off between precision and recall. So downcasing is a recall enhancing technique. It's going to allow us to obtain many more matches for the same query. And so we're much more likely to bring back as potential candidates that we might find as relevant as a user if we've downcased. But at the same time, we're bringing in all this stuff. That also means that there's a good chance that we've brought in a lot of stuff that's not relevant to us. So we're going to be, in effect, lowering the precision of our results to the user. So it's really hard to increase our recall which is the fraction of things, fraction of finding all of the relevant items. So it's hard to maximize that without also then decreasing the precision, which is of the things that we show the user, what fraction of them does the user actually find are relevant. All right, so the next thing that we're going to do after we downcase it in our tokenizer is, and this is the last step basically, is we're going to break the string, break the text, break the document up on non-alphanumerics. So wherever we assign something that's not an alphanumeric character, we're going to say chop that string. Okay, so what are the alphas? Well, the alphas are A through Z, or Z for those, and the numerics are 0 through 9. So those characters. So if we don't see a letter or a number, those are places where we should break the string up. Okay, and sections that are contiguous alphanumerics will keep together as tokens, and everything else will turn into the stuff in between our tokens, which we don't care about. And so we're only going to keep sequences of alphanumerics. All right, so let's take an example here really quickly. This example comes from a piece of text in this short paper, the tokenization paper. So this is why it's basically, I'm going to put it in quotes because this is not my language. They write, we use 2 IR models in our experiments, colon 1. Actually, since I'm quoting them, I should be sure I do it right. 1, probabilistic language modeling. And then it goes on. Okay, so this is just a small example. So if we're going to do this, we're going to downcase it, and we're going to break on things which are not alphanumerics. So our tokens that we're going to produce are just really easily, we're going to go, we use 2 IR models in our experiments. 1, probabilistic language modeling LM. So these parentheses are thrown away. That parentheses thrown away. This semicolon is gotten rid of. Everything is in lowercase. These spaces are not a letter and not a number, and so we throw them away too. All right, that's a quick example of how the tokenizer is going to basically work for us. We will also in the class, and we'll talk about it later today, we'll talk about using a stemmer and removal of stop words. But first, let's look at a simple algorithm to do this. Okay, so this is, you could call it pseudocode, but it is almost entirely Java. But since it's not perfect Java, it's not really Java, we'll call it pseudocode. This is based on Code by Trevor Stroman, one of the co-authors of the textbook. And this is from the Galago search engine that was designed to go with the textbook. We don't ever use that search engine, but we will yank out of it basically one of the simple tokenizers it had inside of it. So let's downcase our text. So this is pretty easy. All sort of languages nowadays have some method to take a string, make it lowercase. Okay. We'll make tokens be an empty list. So this could be, it's like a vector, an array, something that we can utilize, and we can add tokens to collect them as we find them. Let's say start is 0. And then for I is 0, I is less than the length of the text, we'll increment I. And we're going to have this variable C that stores the character at the ith position of the text. And then if C, this is the great pseudocode part, is not a letter or a digit, and then if start does not equal I, I'm doing brace styles in a way to save space on this little whiteboard. We'll get a token out of this by taking a substring from the text. It goes from our starting position to I minus start. Okay. This is just computing a number of characters. So this is we take a substring out of this piece of text from this position forward this many characters. And we take that, we grab it, make a copy of it, and we're going to store that string in our token variable. And then we'll just go ahead and add that token to our tokens. All right. Then we've got that. And then we're going to this place, we advance start to one past where I is. Down that if, down on that for. And then if we've got to clean up here, if start, you have to repeat this. If start does not equal I, then we're going to do there's one last token actually that we need to grab that's it, because we'll hit the end of the string. And so if we hit the end of the string and there's still something there based upon where the start is, so if the start is not at the end, then, oh, there actually was a token at the very end of the string and we need to grab that token. So it's again the same notion where we get a substring from start for this many characters. And at the very end of all of this, we return the tokens. All right. So again, let's walk through this real quickly. Take our text. We're going to lowercase it. We're going to make a list to store in the tokens as we find them. We have this notion of these two indexes that we'll keep, start and I. All right, so let's say that we've got a piece of text which is after it's been downcased, it says MSCI 541. Okay, the idea here is that start comes in and it's basically at index 0, and is pointing there. And then we have I, and I also ends up there, okay? And then what we do is we go and we say, all right, we're going to go into this loop, and we're going to check to see what's at the I position, when I is currently pointing at the start of this string. So if C is not a letter, nor is it a digit, well, it happens to be. So we're down there, we're going to loop back. And so the action there is, oh, while we're seeing letters or numbers, the idea is we're going to be advancing I. So then I moves ahead and looks at the S. All right, it comes in here. Ah, yeah, it's a letter. Well, okay, well, advance I again. And I starts to looks at the C. Yeah, that's a letter. All right, advance the I. We're not doing anything with the start yet. Advance it. It's going to be referring to the I. It's still a letter. All right. And then we're going to advance it, and it's going to be looking at this space in here. And to be clear, we can, when we write strings, we can make a space with this sort of notion there. So now I happens to be looking at this space. So C, yeah, it's not a letter. Okay. Is start set equal to I? The answer is no, it's not. So that means that we started with I and started in the same spot, but then I moved ahead as it went over letters or digits, and then it eventually found something that's not a letter or digit. So now we've captured that we've got a string that we want as a token. So we grab that off, and our first token is MSCI. Wish I could spell my simple acronym. Gosh, too hot in this room. All right, MSCI. It becomes the first token that's added to the set of tokens. Great. Anyways, we've done that. And then what happens? Well, now we're here. And so this shifts start to 1 before I. So start ends up looking at 5. Then we come and do the for loop. And I moves up to the 5. All right, and hey, yeah. Okay, well, again, we got the same behavior here, which is race I on down until it hits something that's not. Again, we'll discover, we found the next token. We'll save that, and then we'll move start up again. If I had multiple spaces here, what would happen is we would end up moving both I and start along until we hit our first letter or number, and then I would move until we hit the end of that token. So this is a really nice, simple tokenization scheme. The algorithm is quite simple to code. We pass in our piece of text that we've gotten from our document, and it'll return us a set of tokens. If you want to save a little bit, make it a little bit more efficient, instead of creating the empty list in here, you could reuse a list over and over, but then you have to remember to empty it back out after you've finished dealing with the tokens there, which is something some students have problems remembering doing. So if you do it this way, you'll be sure that you always have reset the tokens list. But the problem with this is this requires a new allocation for every single document, because this will be a piece of text from a document that you're going to process and tokenize. And so that adds overhead to keep allocating the list and then freeing it, allocating the list and freeing it. Instead, it's better to just allocate it once, be sure it has nothing in it, send it into tokenize and use it, and then it will be filled with the tokens. Use them in your indexing and other processes, and then reset it. It won't free up the memory, but it also won't have to allocate more memory, and then you can just reuse it and send it into tokenize again. It's not a hard idea. It's a small optimization. I hate to talk about those things because then people focus on them, but I did want to mention that we try, if we can avoid allocating and deallocating over and over and over again. Usually that's a good idea, but it's a really minor thing for the efficiency. It's not. In other words, this is the type of thing that in your algorithms and data structures courses, when we talk about the constant factor, that's exactly what that is. That sort of optimization just changes the constant factor. It makes it run a little bit faster. Doesn't change the algorithmic complexity at all. I mean, that's a nice linear algorithm. Okay, so there's nothing that would change that. All right. So what is this overall text processing pipeline that we're going to be dealing with here? So let's take a little bit closer look at this. All right, this pen is on its way out. So that says text processing pipeline. Basically, what we're going to do is you've got a piece of text. So this is something we've grabbed from a document. In our case, we're going to get these from these text documents. Again, it'll be the text that is a combination of the text field, the headline, and the graphic tag. But then we're also going to need to strip out the extra tags in there. So there'll be a bunch of paragraph tags, for example. These paragraph tags are tags that are just like a letter P. And you don't want them, otherwise you're going to have all these tokens with the letter P everywhere. So it's pretty easy to write a little bit of code to strip those tokens out. You can easily Google how to remove HTML tags from text or something, and you can get a way to process and remove them. Anyway, so we're going to take text. It's free of our tags, so we can think of this as just, it's that string, it's got a punctuation and all this sort of stuff in it. Then we're going to send it, we're going to process it with the tokenizer. That's going to produce for us a set of tokens. Okay, so again, this is for us, our tokenizer. Our tokenizer is all about downcasing or use lowercase. And again, we're going to maintain that our strings are strings of alphanumerics. All right, we're not going to try to separate the letters and the numbers if they're touching. Then you can go to a process known as stopword removal. So stopword removal, its idea is to remove common words such as a and the and of, etc. There might be several hundred of these that are typically removed from words. We'll talk about this and whether to do it or not, but it's usually, if it's going to, so take your text, break into tokens, look at those, maybe throw some of them completely away because you didn't like them. Then put it into to stemming, and where we apply, this is a stemmer. We should apply the stemmer to produce stems. All right. So another, this is a notion of conflation. And again, the example I gave before was about run, runs, running, runner. They all have a stem of run. And so we would take a word and say, ooh, can we reduce it to its stem? And that meaning that all those different types, different varieties of that word are conflated down to one single form, the stem of that word. Again, that is a big recall enhancing technique. The idea is to increase the ability to find matches in these documents, because why should plurals, for example, prevent you from finding matches? Oh, I'm really interested in buying a new bicycle. Oh, and then this web page talks about bicycles. We sell bicycles. Well, if we don't fix that plural in that web page, we're not going to find a match between my bicycle in my query and the bicycles in the document. And so that conflation is necessary if we want to be able to enable that sort of match. All right. And then the final result is this heads off to our indexer. So the thing that's going to build the index for our system. And again, the index is going to, the primary purpose is to speed up the running of the ranking algorithms. All right, so that's the basic pipeline. Let's take a look in more detail at stopword removal. So again, stopword removal, this removing of common frequent words, all these articles, a, of, the, and so forth and so on. What advantages might we have for doing this? Well, it does save some space in the index. So if we throw these things away and we don't bother to put them in the index, we're not going to write them out again. That very clearly is going to save some space. With really big collections, it's always great to save space. We're always we can always be short on space. Likewise, we're often short in space in memory in RAM. In particular, and if we have to bring in structures from the index into memory, and those are large and numerous, that could be problematic for us. So that can be a nice little savings in space, but we're really usually talking about the index. Getting rid of stopwords can improve the speed of retrieval. Because we're going to end up never processing these words when they're in a query. Okay, and in particular, we're in the index that we're going to end up building. What we do is we have a single word, and then we record all of the documents that contain that word. And when we do our ranking, we're going to say, oh, the user gave me this word, and we're going to go fetch that list of documents. And we're also going to we're going to do that for every word that the user gave us. So if the user types in, the word the as part of their query, we're going to fetch a list of documents that contain the word the. And we're going to consider them as candidates to actually, should we show that document to the user or not as part of our ranking algorithm? Well, almost every English language document contains the word the. So all of a sudden, we end up having to compute a score for basically every document in the collection, which, if the collection is large, could be really problematic for the amount of memory that we have. It could be just super time consuming. Our goal is not to actually have to compute a score for every document in the collection. We'd like to only compute the scores for the documents that are good candidates that the user might find to be relevant. So this has the real potential to speed up retrieval performance for users. Now, that being said, there are algorithms which are smart and wise about, even if you have a word that's highly common, they'll know that it's not very useful. And it may be able to stop processing of such a list of documents based upon that not very useful word earlier than we might expect with a more naive ranking algorithm. So there are techniques to deal with this. We're not going to cover them. So certainly it could very well be nice for us to remove stop words. It'll turn out though that the queries that we use in this class don't really suffer from a lot of stop words and issues like that, and so it's not something that we would run into, but it's for a real search engine. Absolutely, you're going to have questions about this. All right. What else? So stop word removal can improve the quality of our results if our ranking algorithm that we're using does not deal well So the ranking algorithm might not actually be able to understand how to properly sort of ignore the stop words. Again, they're so common, but if it doesn't actually handle that properly, it might mess up our ranking. And so documents that we wouldn't normally consider might get pulled up high into the ranking, and the user goes, what are these doing here? And and these are non-relevant documents, and they're going to hurt the precision of the user's experience using the search engine. It's going to slow down their ability to find relevant material. So it's quite possible that it can actually improve the quality because the ranking algorithm doesn't need to deal with this concern. Now these are all actually advantages. So here's a disadvantage for stop removal, is that it can hurt queries, which is really, when we say it can hurt queries, it's going to hurt the end user who's trying to find information to help them satisfy their information needs. So this can hurt the queries that require a stop word. Like what could that be? Well, examples. Classic one from my supervisor, James Allen, was vitamin A. So imagine, A is an article. It's likely to be in every single stop word list because it's so common in the English language. So if we take this query, we tokenize it, we end up with the word vitamin, the letter A. We go, oh, time to remove stop words. Is vitamin a stop word? No. Is A a stop word? Yes. We throw it out. So now all we're left with is the word vitamin. And now the poor user who's trying to find information about vitamin A is forced to wade through all the documents that only mention vitamin. And it's like, well, this is talking about vitamin C. I wanted vitamin A. Why won't that search engine pay attention to me and give me documents about vitamin A? Very frustrating for the user. I mean, I believe there was a band once called the. Yeah, imagine if you're a user and you're trying to find information about the, and stop word removal is turned on, you're not going to be very happy. So what do we really do in practice? Do we remove stop words, not remove stop words? Well, in general, it seems that what we can do, because space for the index and disk space is not really that big of an issue. We have such large storage space on hard drives now. So in general, we leave stop words in the index, but remove them as appropriate from the query. So, oh, how in the world are we going to figure out that we need to remove A from this, the letter A from this query, but not from the query vitamin A? I don't know what to say about that, but we can, if we do keep them in the index, we can then allow the user to require a stop word. So the user could certainly be like, no, don't remove this word from my query, use it. And then we're like, okay. And we use it and we help the user find what they're looking for. Sure, the retrieval might be a little bit slower, but that is way, way, way better to the user than you've produced garbage results for me. This puts the burden onto the user. But I mean, if it can be made clear, you know, oh, we've removed this word to include it, click here. Oh, okay, I want that form of the query. Or if it was removed and it's like, yeah, I don't care if you removed that word. And what do you mean? Like, all right. If it's easy for the user, maybe it's not that bad of a solution. All right. Now, what about this stemming? Well, there are two big ones that we see in research. Certainly, web search companies have their own proprietary stemmers. I still remember Amit Singhal coming to University of Massachusetts and giving a talk. Oh, this is probably somewhere like 2004, 2005, I don't know. And one of the things he recounted was absolutely that it took Google a very long time to figure out a stemming scheme that they felt was actually good and appropriate. So for example, on the web, we just have huge usage of language and terminology and all sorts of punctuation and stuff. I mean, I even just think about, for example, like back to the tokenization problem. So if you have a language like C++, the early web search engines did what I was saying, you know, had very simple tokenization schemes, and all of a sudden you do a query and you're looking for stuff about C++, and these non-alphanumerics were wiped away, and it turned into the letter C. Okay, great. Now you'll find web pages about, let's say you had some other query terms in here about programming languages or something you're looking for, all about the C programming language, intermixed with ones about C++, but you could never focus in on C++ because of the tokenization scheme. So that web companies, in dealing with stemming, Amit said it was very tricky and it took them a long time to find a scheme that they felt worked really well. For us, we're dealing with these traditional newswire articles for our retrieval situation. Stemming certainly is applicable. You know, it's just some basic language being used in newspapers. All right, it could actually help us to find what we're looking for. And this is thing to keep in mind is that whenever we're building a search engine, the quality of it needs to be measured with regard to, you know, actual human usage. Whatever the documents that we're doing might be different than another search engine. The user information needs and the queries that come in will be different. And so we need to be able to evaluate and design our system appropriately for the people that we have using it and the documents that are in it. Nevertheless, stemmers, there's two widely known ones and widely used ones, especially for the research community. One is the Porter stemmer, which has been around a long time. Porter gives these examples that all have the stem connect. So you've got connect, you've got connected, you've got connecting, you've got connection, you've got connections, plural, etc., etc. So all of these have as a stem the word connect. Anyway, so Porter is really big on a mechanism that uses rules on properties, common properties of the English language, and basically has the rules often know how to chop off the end of a word in some fashion to result in what will be the stem. So one of the problems with it is that it can produce non-words. So you started with a word such as abusing, and it'll get stemmed to a bus. I mean, it's not an English word, so as far as I know. The real stem, you would, of course, should be abuse with an E on the end, but that's not what the Porter stemmer turns it into. So, you know, and you're like, well, who cares? This is just the internal representations, the index terms for the document. Well, there are times in which we want to be able to show things about the way the algorithms are working to the user. We might want to, there's all sorts of things. We might want to there are these things with query expansion and similarities, this and that. We might end up being like, oh yeah, I want to use, find the most important words in a document and show that to the user. And our representation, if we've used Porter stemming, produces all sorts of non-words that we don't want to show the user. So that's a downside. From using it, and does it help retrieval or not, Porter stemmer often works really quite well. It's actually quite aggressive, so there's a lot of conflation at hand. In general, it works quite well. The other commonly used stemmer is the Krovitz stemmer. Both of these are named after their creators. And the big thing about the Krovitz stemmer is that it uses an English language dictionary to only accept stems that are words. So it has a bunch of internal rules like Porter does on how to stem, and when it says, oh, I'm going to try to make a stem via this set of rules, it then produces a stem and checks the dictionary, and the dictionary goes, no, that's not a word. Oh, okay, well, I'll apply some other rules to stem it. Did I get a word now? Oh, you did. Okay, that's the stem I'm going to use then. So it works very hard to try to keep them as English language words. Now, what we're going to have tokenization that has alphanumerics in it. What does Krovitz say about a word that is a combination of letters and numbers? My guess is it's like, I don't know what to do with it. Maybe it doesn't touch it at all. So these are things, all of these parts that we put together, they're all interacting. So we start with this huge amount of data, with all these documents. We start turning it into all these words, and we have all these processing steps. They're all interacting with each other. This is a very complex system, especially because of the amount and the variety of the data to actually optimize and improve. And so it's one of the reasons there's so much research on it. Thankfully, because we can measure quality, we've been able to make lots of progress over the years on this. Some notes about, so stemmers, again, they are a recall enhancing technique. So stemmers one thing to note is that they can conflate very different words. to the same stem, which is something you might not be thinking about happening. So for example, you could take the word organizer and these will get stemmed to organ. So you're searching for something about an organizer, and instead we're getting documents out about organs, either the musical instrument or, human organs and things like that. And all right, we'll still find the documents that contain the word organizer, because all of those documents will have had those words stemmed to organ, and we'll get those matches as well. But we've just ended up lowering the precision of our results often through this mechanism because we did stem organizer. Okay, so now's time. Now we've gone through tokenization, stopword removal, looked at stemmers. Let's actually look at this little 2-page paper. It's in Learn. The influence of basic tokenization on biomedical document retrieval. Now, in this paper, they run a set of experiments, and we haven't talked about how to measure quality yet, but they measure retrieval quality with a measure called mean average precision. The measure itself is average precision. The mean part is that they are averaging it over all of the test queries, the test topics in their test collection. And so because it's kind of strange to say average precision, we say mean average precision, or MAP. It's a very old evaluation measure. We will talk about it in much more detail. For now, you just need to know the bigger the number, the better the retrieval quality. It's a measure that works in that manner. Now, they do this. They have 2 collections that they have in this paper. So the focus is on, as the title goes, on biomedical, but they also have a collection, which is a standard news collection, which is going to be very similar to what we do. I think actually our LA Times little collection is a subsample of their larger news collection. So they have this one called the Genomics, which does biomedical search tests. And then we're going to look at news. What I'm going to do right now is start to write up some of the schemes that they have. And they also have 2 retrieval methods. One of them, language modeling, or LM, as abbreviated in the table. And the other one is TF-IDF, and which is, I don't know if they even specify. It's the out-of-the-box one from Lucene. So that's some sort of a cosine similarity type traditional thing. Lucene now actually has gone to BM25, is my understanding. Anyways, which is also TF-IDF-y, but is more sophisticated than the older versions. That probably was what was in Lucene at the time. So let's focus on the LM numbers, the language modeling numbers. So we'll talk about a tokenization scheme, and then I'm going to give the numbers for their genomics results. Actually, I'm going to need more space. So the scheme, and the numbers for the genomics, and then the news, which is similar to the work that the collection we're going to use. So they start off with their sort of the most simple scheme they call the LL scheme. And the LL scheme is just simply to lowercase letters. And basically, wherever I have a string, So they lowercase the text, and wherever I have a string of letters, that's a token. Anything else is not part of the token, and so we break it up in that fashion. All right, so then they measure this, and they find for genomics that they get a score of 0.3. I'm going to actually only go to 2 significant digits, and for news, 0.17. There's a bad habit in a lot of information retrieval papers where they'll report these measures out for 4 significant figures, and that's ridiculous. Now, these authors very nicely use statistical significance testing as well. You can often go out to 3, maybe realistically, but 4, there's no reason for it. 2 significant figures actually kind of goes along with what we will see, what ends up being significant or not significant. So this keeps the numbers simpler. Anyway, so this is sort of their baseline. Like, can we get any simpler than just, I want a sequence of letters. I'm going to throw away all the numbers. I'm going to throw away anything else that could be of use. In particular, they're concerned in genomics with things, the biomedical type things. There could be Greek letters, all sorts of fancy ways to express, I'm looking for this thing, health-related information. And then the tokenizer, it's like that C++ example. If it's not smart enough, it can just throw away extremely valuable information given by the user. But also, there's a lot more ways that a user might express something that it wouldn't actually match what's in the document. So if someone has some way of like copying and pasting a Greek letter into their query, but in the paper, it's not written as a Greek letter, it's not going to match. Or more likely, the user doesn't type in a Greek letter, they spell it out. So instead of putting in the Greek letter kappa, they spell out kappa, K-A-P-P-A. But in the paper, it doesn't spell out the word kappa. It's because it's a fancy PDF document that's nicely typeset for a journal. It might very well just only have the Greek letter. So how are we supposed to match that? Well, you want your tokenization scheme to come up with a way such that the kappas, however the user presents them and however they're presented in the document, will find each other and be a match rather than a mismatch. Anyways, lowercase letters, trivial. These are our baseline scores with the language modeling methods in that way. Then, I don't know why they called that was the baseline, but then they're like, well, let's just do letters only. Let's not lowercase them. So this is not lowercase, okay? So we don't change, we keep things case sensitive, and this hurts performance, but it does not hurt it at a significant level. So it reduces it, but they report these aren't significant reductions. In other words, over their test set, this could just be statistical noise, so to speak. Anyways, so it seems to be better to downcase. Maybe there's something there. Then they look at, they call this LLD. This is where this is basically our tokenizer. Okay, so this is, we're going to lowercase or downcase, and we have letters and digits, and we let them stay together. We don't try to break the letters and numbers apart. So for the genomics, we get a small improvement. Again, not statistically significant. Goes up to 0.33. And then for the news, back up to 0.17. Okay. And you could, there might be some notion that you can start to see why it might be good for genomics, because people are typing in fancy things with letters and numbers. They have examples here, and you can take a look at them in the paper. They're in the table. Their next scheme that they apply is, again, let's just do this, but not lowercase. So not lower but it is letters and digits. All right, then this guy ends up at 0.29. Seems, again, the not lowercasing it is hurting things. All right. Then they have some other schemes. I'm going to skip over them. Okay, so let's look at LLP. So this is LL plus Porter stemming. So we're going to use only letters. They're going to be lowercased, and then we're going to send those tokens into the Porter stemmer, and we're going to see what we get back out. For genomics, this takes us back up to 0.33, but it's still not statistically significant improvement. And for language modeling, we're back up to 0.17. We still haven't done anything. So they're reporting here that if your base scheme is just to use the letters to form words or tokens, and then you Porter stem, at least on their news collection, there's no improvement to using stemming. Okay, same thing with genomics. There's no proof here that stemming is of any value or usage to that. Does it mean it's of no use? Well, depends on whether or not mean average precision is the right measure for our system and so forth. It depends upon whether, are the queries that we're using truly representative of our users? For this experiment, we will assume that yes, we have the right queries and documents and we have the right measure. And so yes, this result for this one experiment says with this base level of tokenization that stemming is not useful to us. Okay, then let's go ahead and we'll do maybe stop words. So we'll use the LL with stop words. So we'll do the LL and then we'll remove stop words. Okay, so this is really quite, this gives us, boom, we're up to 0.35 and it is a statistically significant improvement. Likewise, even though this is 0.17, there is some statistical notion that this is better than this 0.17. I'm just going to skip ahead in the course right now. Just because you've got a tiny improvement and that's statistically significant, is it a significant improvement? The answer is no. It's not a significant improvement to the user. There's no difference effectively from what the user would ever see. Sure, statistically, there might be down in the lower digits some improvement, but trust me, the user would never see this. So we got to be careful about when we analyze and look at results. We'll talk a lot more about this. Then they go and they try some wild schemes. They say, let's just break on non-white space. Or let's make tokens so the tokens are non-white space. So, by the way, that includes all the punctuation and everything. Like it's just anything that's not white space becomes a token, and it's all stuck together. So if you have a period at the end of the sentence, that becomes part of the word. That sounds crazy. Yeah, so this drops all the way to 0.17. This is a huge drop in performance. This drops all the way to 0.12. Also a huge drop in performance relative to the baseline. This is like a 27% drop. This is 40 some plus. This is a bad tokenization scheme. Don't do that. This tells us, yeah, we wouldn't want crufty tokens filled with garbage. All right. Then, let's actually lowercase this one. It also doesn't solve that one. Then they create what they call a compound tokenizer, and this one's pretty interesting. they're going to split on white space. So white space are things like spaces and tabs and so forth. They're going to remove non-alphanumeric. Then they apply they've got one, oh, I didn't actually list it, I should have, the SLLD. All right. Now, what's interesting about this, I'm going to erase this. What's interesting about this methodology that they come up with is they give an example. It's better to see it in form of an example. So they say, you know, if we have something like B/CD dash CD 28 dash responsive. So this is a very, you know, biomedical type thing. B/CD 28 dash responsive. There could be potentially all sorts of ways that users put that in. What they do is that this gets turned into one token that gets produced is the BCD28 responsive. It basically throws out all of the non-alphanumerics and glues that together. It also then goes in here and then runs a more regular form where it goes, oh, I'm going to split on all this stuff in lowercase. And so then you get a B and a CD and a 28 and a responsive. Okay, and these are all the tokens. So from this one string, we don't just break it into a series of tokens. We also include a token where we've glued it all together. And the nice thing about this is if a user was to type in this sort of thing as a query, great. We've gone and we've produced both of these for the users. But if the user like chooses some other thing where maybe they include some spaces in here, well, the great thing is they include those spaces. We won't get this string, but we will get a lot of these strings down here. So we still have a chance for finding a good match with documents. So it's basically, one of the neat things here is this idea of like, it's not just a string and it's chopped into certain tokens and we throw away stop words and we convert to stems, but you could even envision schemes where we both have the stemmed version and the non-stemmed version, and we index both of them. We keep both of them around so that we can potentially leverage some of the precision and recall enhancing notions of these tokens. So I think this is it's sort of a I create more tokens than we might normally be trying. Almost everything else is recall enhancing. This is a combination of recall and precision enhancing here. And so that is really neat. And then by the way, this then actually, when they do the compound tokenizer for the genomics, it goes up to 0.37, and then for the news, we're up to 0.18. These are rounded up. This is a small statistically significant improvement. Again, whether a user ever noticed that, I don't know. This is quite a big improvement, whole 5 percentage points, so to speak, but it's not statistically significant. So, but then they go, oh, let's go one more step. And of course, this is the piece de resistance of their paper. This is their custom tokenizer. And so they're like, you know, this is the kitchen sink. They're going to throw everything that they've seen that was good in what they've done before. So they're going to take their compound one. They're also going to throw in Porter stemming. They're also going to remove stop words, and so forth and so on. And so you've got stuff here. They even got in here these Greek letter translations they have. So, all right, I throw all this stuff in, and now this does get them up to 0.40. And so this gains them this is a 27% improvement, and it's statistically significant. So compared to the simplistic tokenization schemes, a more sophisticated tokenization scheme, especially designed in their mind for the genomics track, this biomedical track, they're able to get a 27% improvement. Now, it is a really good chance that users over the course of using a search engine repeatedly might actually be like, I really like this search engine more than one that was built with this tokenizer. The ranking algorithm could be the same, all sorts of things could be the same, but it's the tokenizer that has changed because it's able to use index terms which are more meaningful and which enable, from the user's query standpoint, to actually find good matches. So the whole thing together works out. And by the way, for the news, what's really nice about this is their custom tokenizer gets them up to 0.21, which gives them over here a 23% improvement, which is also statistically significant improvement. And again, that's it's 4 percentage points. Maybe it doesn't seem gigantic to you, but imagine if you were Google and this was spread out over, this sort of improvement was spread out over millions of queries a day, and to say that, yeah, boss, we've improved things 23% for the user population. Wow, thank you, that's great. 23%. This is a relative improvement. The 0.4, the 0.04 difference between these would be an absolute improvement. But so the relative improvement is 23%, which is, so that's a really nice improvement. And all they've done is worked on their tokenizer. And so tokenization does matter, and the choices with stemming and stopword removal can matter. And part of what's nice about this is they're showing that small things on their own might not be beneficial, but when we pile them all together, the end result might actually, all of them coming together might result in an improvement that's not very noticeable on their own. So we might very well, if we'd run this experiment with the Porter stemming, go, stemming's no use. But it wasn't until they added in things like the stemmer into their compound one to produce their custom one that they actually got what was a statistically significant improvement, and that's pretty neat. And I think that's really speaks to the notion of why we care about how we actually turn documents into tokens that we're actually going to index. And it all goes back again. It's like the manual way for the humans doing it. It mattered which words the librarian picked. So it matters even how we automatically chop up and choose what to label those documents, which then feed into the algorithms that are going to do the ranking for us. And so it's all interconnected, but these decisions can impact the performance of later algorithms.